Starting with the learning outcomes of the topic, and then basic term steady state error. We will define and also define the factors on which these type of errors are dependent. And starting with the unity feedback systems, and ultimately we will also study the steady state error for non-unity feedback systems. Most important terms of the topic is static error constants, and this is also covered in this lectures, and the factors of these static error constants on the steady state error also this is in this lecture. The linear control system is divided into three major parts. First one is the modeling. In modeling we covered how to mathematically model mechanical or electrical systems or electromechanical systems, and also representation of these systems in time domain and also in S domains. If we represent the systems in differential form, then how to convert the differential form by applying the Laplace transform into a S domain representation. And also there are other representations. After covering the modeling, we start the analysis part by the discussion of transient analysis. In transient analysis especially, we derive the specific relations to define the specific parameters which will be helpful to design the systems. So first order and second order transient analysis is we study in deeply, and then is the stability. And next part is the steady state error. This steady state error is also helpful to design the systems. If there is error, then how to remove this error and make the systems error free. So let's see. So in linear control systems, so another important terms which will be helpful to analyze the systems, and definitely it will be helpful to design the systems. So this is the steady state errors. To understand the basic definitions, let's review the generic diagram. So in this block diagram, there is this controller. In this case, if we take this k is equal to 1, and the g1s is the open loop transfer function, and r of s is the input value, and c of s is the output or desired value, and e of s at this point is the error signals, which is the difference between the input value and the values coming from the feedback with negative feedback. So in our case, systems is unity feedback. Here h of s is equal to 1. So at this point, value of the feedback is only output value, which is the c of s. So e of s, which is the error signal, is equal to r of s and the difference of c of s. So what is mean by the steady state error? So if the system is stable and linear, then steady state error is the discussion of the difference between input and the output value at time equal to infinite when system attain its steady states. So this is the basic definitions, and factors which are very important for the steady state error are the nature of the input. So if we change the input type or if we use different type of inputs, system behavior definitely will be different. And type of the system is also important part for to study the steady state errors. And there are also nonlinearity of the system components. So these are the three major factors. Due to these factors, there is some steady state errors. So before going to start the detailed discussion and derivation of steady state errors, let's review the basic terms. What is meant by the system type and the order of the systems? System type actually defines when there are poles at the origins. If there are no pole at the origin in a complex plane, then this is the zero type systems. If there are one pole at the origin in a complex plane, then this is the type 1 systems, and so on. And what is meant by the order of systems? So total number of poles in a systems is the order of the systems. So let's review in detail. First, review the order of the systems. So for example, we have a transfer functions. Here this is the b, m and an are the coefficients of the polynomial of numerator and the denominators. So there are two polynomials, b coefficients representing the polynomial of a numerators, and the denominator parts are represented by with the coefficients of a's. So if we want to find the order of the systems, then highest order in a polynomial is n. So in this case, order of the systems is s, is n. And for example, if we take a transfer function like 5 over 2s plus 1, then in this case, what is the order of the system? Because in denominator part, maximum power of the s is 1, so order of the system is 1. And similarly, in the second case, next transfer function have the 15s over s square plus 2s plus 1, it is the second order systems. And similarly, next one is the fifth order of the systems. So to understand the system type, we take the open loop transfer function g of s times h of s. Now currently we are taking the unity feedback in which h of s is equal to 1. Later we consider h of s is not equal to 1, so definitely it will be non-unity feedback. How to handle the non-unity feedback we will see in later. So system type, in this case, in this term, s raised to power c is extra from the previous case. So in this case, maximum order of the polynomial is s to raised power is n, and this s representing the poles at origin. There are number of poles c at the origin. So what is meant by the system type? It defines C is the system type. And what is the order of systems? Total number of poles is the sum of the power of poles s raised power c plus maximum power of the s of the denominator polynomial is n. So total number representing the order of the system, which is equal to n plus c. So let's see in this example. Similarly, we revise this example. In this case, it is the first order systems because maximum power of the s in denominator part is 1, and this is the type 0. It means there is no pole at the origin. It means we can represent s raised to power 0. There is 0 pole at the origin. And similarly, in this case, there is 1 pole at the origin. So this is the type 1 systems, and total s raised power is 2. So it is a second order system. And similarly, the next example. So it defined the type of the systems. So next important point which is necessary to review is the input type. So there are many input types, but we're taking the few inputs. So in steady state error, actually steady state error is the difference between the output and the input. So input is very important in these cases. So first input is the impulse function. Sometimes it is a unit impulse if there is a height is unity. So physically interpretation, actually it is representing it present at a specific point in the time domain. And mathematically definition, this function is exist when delta and this argument is 0. If t is 0, so then this function exists with the height of a, and the Laplace and otherwise it is 0. And similarly, Laplace transform of this function is a. So next one is the step function or a unit step function. This blue line representing the step function. If the height of this function is 1, then we can say this is the unit step function. This is also used to analyze the steady state error. So physically it is a constant value for all the times, and the definition of the function is this function exists for at the value of 0 and for greater the value of greater than 0. So for time less than 0, function value is 0, and Laplace transform of this function is 1 over s, which is very important, and we may use to analyze the steady state error for different type of systems. RAM function is the next text waveform to analyze the steady state error, and this is the constant velocity input to a position control systems by increasing the amplitude. So this is the definition. This is simply a function of t, and where a is the constant, and this ramp function is unit ramp when this a is equal to 0, and the Laplace transform of this one is 1 over s square. Parabolic input also used to analyze the steady state errors, and this is the constant acceleration, and this is the representation of a function a over 2 times t square. So if a is equal to 1, then this is the unit parabola, and the Laplace transform of this function is a over s square, and 2 value of 2 is cancelled out, this value 2, and this will be cancelled out, and Laplace transform of, for example, is equal to n factorial over s raised to power n plus 1. So this is the next input waveform which is used to analyze the steady state errors, and the Laplace transform of unit parabolic is 1 over s cube. These test signals are actually related to each other in a given pattern. For example, this is the impulse, and for unit impulse small a is equal to 0, and it exists only a single time. In this case it is time equal to 0, otherwise its value is 0. And the next is the step input, and the function of step input is exist at time equal to 0 and greater than 0. And similarly, next one is the RAM input, which is the constant velocity, and next one is the parabolic, and this parabolic is unit parabolic when a is equal to 1. So if we integrate the impulse function, we get a step function, and similarly integration of the step function represent the ramp function, and similar way we can find the integration of the ramp function gives the parabolic. And reverse process is simply if we take the derivative of this one, which is equal to step function, and similarly derivative of this one is the derivative of the ramp function is the step function, and the derivative of the parabolic is the ramp function. So this is the relationship in time domain, as well as these relations also exist in the Laplace domain, which we use in this chapter, which is steady state error. Let's see how will we use. Let's review the next and important behavior of the LTI systems. For example, we have a LTI system here, and if we apply some impulse input, and the output will be like the impulse function, but it is not an impulse. The response is variable as compared to the input. This is due to the behavior of energy storing components. For example, in electrical components, capacitor and inductor are the source of this type of transient behaviors. And after the transient behavior, systems becomes in a steady state, and now our topic is to analyze the steady state values, actually to find the errors at steady states. So transient response versus the steady state response. Actually, transient response we observe, which is only depends on the poles, but if we change the input, the value of transient response is not very. So usually we check the behavior of transient response by using the simply step input. As compared to transient response, steady state response actually depends on the different factors like dynamic of the systems and the system type, actually, and the input of the systems. So if we change the input, the steady state response definitely change, and its value can be found by using the final value theorem, as we'll see in the next coming slides. So to understand the steady state error, let's visualize the concepts. First of all, for the step input, so this black horizontal line representing the time axis, and similarly vertical axis representing the magnitude. So blue line representing the input. For example, if it is a step input, then definition of the step input is at time equal to and time equal to 0 and greater than 0, value is higher than 0. If it is unit step, then height of this one is equal to 1. For this step input, here we have two type of outputs. One is the green color representing the one type of output, and other type is representing by the red line. It's the second type of output. So in the starting, as we apply the step input, transient behaviors is appear in the starting, and as the transient behaviors vanish, then behavior of the steady state is easily observed. For example, at this point, if we see that input and output are coinciding, it means there is no difference between the step input and the green color type of the output. So after transient behavior, steady state behavior is observed, and there is no vertical difference between the input and output for the green color. It means steady state error is 0. So C1 is representing the first output at time equal to infinite. So this representing the output for first response is equal to 0 as compared to the second one. In this case, after observing the transient behavior, for example, in this case transient behavior is almost up to here, and after that behavior of the systems for step input is almost constant, but it is not approaching the input. So this is the vertical difference between the input and output. This is the steady state error. So in this example, we visualize the concepts of steady state error. For single input, there are two types of output. In the next example, we visualize that three different categories of the steady state error. So in the next example, if we want to observe the steady state error, and here input is the RAM input. Again, this is horizontal axis, which is the time axis, and similarly vertical axis representing the amplitude, and this blue line representing the input, which is the RAM input. If we apply the RAM input to a systems, and if we observe three different type of output, for example, in our case we have first is the green input and green output, and similarly this yellow input is the second one, and similarly red is the third type of output. So in transient response, after the transient response, if we observe the steady state response, for example, for first type of output, after at time equal to infinite, for example, in this case this is time equal to infinite, and if the input and the green output difference at time equal to infinite is equal to 0, it means steady state error is 0 for this green output. It means it coincides after the transient behavior with the input. And similarly, for second output, input and output make a constant difference after transient behavior. It means there is a constant difference between the RAM input and the corresponding output, which is representing the yellow color, as we observed in the previous example. And similarly, third output is increasing at we observed after transient behavior as well as at time equal to infinite after the transient behavior. Even in steady state, this difference is increasing. For example, if we observe the vertical line here at any time, then this difference is increasing. It means difference between the input and the corresponding output in red color is increasing its value at time equal to infinite. If we observe at time equal to difference, this difference is equal to infinite. So in this case, steady state error is increasing, and we simply say it is approaches to infinite. Now we want to find the definition of steady state error from the block diagram. This R of S representing the reference are the input value, and C of S representing the output value, and G of S representing the open loop transfer function, and E of S is representing the error signal, which is the difference between input and the output. In our case, first of all, we want to observe the unity feedback. If it is not unity, then it is another case we will study later. For example, in this case, H of S is equal to 1. So this C of S is actually representing, in this case, is value at this one is equal to C of S. So all this is equal to in the frequency domain. So error signal is equal to the input and the output, and also we observed that output is equal to error signal times the G of S, open loop transfer function. If we put the value of this C of S in the E of S, then E of S is equal to minus E times G, and if we take to the left hand side, then E error signal is 1 plus G is equal to input signals. So this error signal is equal to this one, but this error signal in the frequency domain, our definitions actually steady state error is observed in time domain. So if we want to find the error signal in time domain, especially at time equal to infinite, so first of all, to take the inverse Laplace, then this relation representing automatically in time domain and then at time equal to infinite we can find the steady state error. Another way to observe the steady state error is to apply the final value theorem. What is the final value theorem? If we want to find in the time domain and the relation and the output is in frequency domain, then this definition is applicable. So this is the final value theorem. This is very important. You already observed in signal systems and also in circuit analysis too. So steady state error, E sub SS representing the steady state error, and this infinite is time equal to infinite. So this is the definition of steady state error, and our relation is in frequency domain. So if we want to find the value in time domain, then we have to apply the value, multiply with the S, and then apply the limit, and it is actually opposite in time domain, also in S domain, then S approaches to 0, then this steady state error is like this one. This is the definition of steady state error in terms of input R of S and G of S with unity feedback. So this definition is very important. Keep in mind, it will be, we will use in our topic continuously this relation and also another relation. Just to visualize the concept in deeper way, for example, if there is no unity feedback, H of S is not equal to 1, it is else 1, then this steady state error relation just we can observe by the change if this G of S is multiplied by the H of S, and just this small variation will be also represent the steady state error for non-unity feedback systems. So steady state error is the difference between the actual value and the desired value. It means input and output difference at time equal to infinite is representing the steady state error. So this error signal we can find in time domain by using the inverse Laplace of this one, or if it is time domain, then we take the Laplace transform, then this is representing the error signals. And for unity feedback, it is already observed, and also for the non-unity feedback systems. Definitely we can drive the final result for steady state error. For unity feedback, it is already observed, and for non-unity feedback systems. So another view to observe the steady state error. In this case, if we have closed loop transfer function, for example, T of S representing the closed loop transfer function, then the block diagram is slightly different from the open loop transfer function. So it is forward feedback. So this is the R of S is the input and C of S is the output. So this is the input and this is the output, and this is the closed loop transfer function. And if we want to find the error, then this is the difference between the input and output. If we take the input from here and add in this junction, and output also taking with a negative sign, then this error signal is representing by this one. So this error signal is the difference between input and output. And the C of S, what is C of S in this block diagram? It is actually, if we want to observe the definition of C by R is equal to T. This is the transfer function, definition of the transfer function, and the C of S is R times the closed loop transfer function. And if we substitute this value into in this one, then we have C of S error signal is equal to R minus R times closed loop transfer function, and this is the final relation of the steady state error. But this is the infrequency domain. If we want to find the steady state definition of the steady state error in time domain, again we have to apply the final value theorem, and the value of the steady state error according to the definition, just multiply with in s in frequency domain and apply the limit s approaches to 0, and this definition will be equal to representing the steady state error. This is the definition of steady state error. Up to here we have two type of definitions of steady state error. One is in terms of closed loop transfer function and other is s times, and this is the another definition. Both definitions will be applicable if the uh, transfer function is given in open loop as well as in the closed loop transfer functions. Okay, to review the concepts of steady state error, let's see the example. For example, input is 1 of s is, and this unit step function is if applied to a closed loop transfer function, which is 5 over s square plus 7s plus 10. Actually, this system is representing like, for example, this is the r of s, and this is the closed loop transfer function, and this is the output. If we want to find the error in steady state at time equal to infinite, first of all we have to find the steady state error in frequency domain. At as we observed already observed that error signals can be found from this one. If we take C is negative and this input is here, then we can find the steady state error. So definition of the steady state error is already derived, and from here if we want to find the value of this one, for example, without taking the limits, and let's s is the by definition and r of s is the unit step, which is 1 over s 1 minus 5 over s square plus 7s plus 10. If we simplify this relation, then we have the value of steady state error is this one. Actually this is not, it is equal to s times. So if we apply this relation here and apply the definition of this one, if we apply the limit s approaches to 0, so this is going to 0 and this term also 0, so it is equal to 5 over 10. So this is the steady state error in our example. So this steady state error is actually constant. If you people understand the concept of this example, definitely complete topic will be automatically understandable for you. Okay, let's observe this closed loop transfer function is the second order, and type of the system is zero type. So what will be happen if we take this type 0 systems into a type 1 systems. What will happen? It's your task. Try this one, and what will be the steady state error? Then you have to find this one. And let's see in the next examples. So up to here, steady state error for closed loop transfer function. In terms of closed loop transfer function is simply, so this is the error signals, and this is the error signals. And similarly for open loop transfer function, error signal is simply this one. And if we substitute these error signals in this relation and find the steady state error, just because steady state error in time domain, so this is at time equal to infinite. So in frequency domain, just apply the final value theorem, so it is s times the error signals. So up to here we find the steady state error in terms of closed loop and open loop transfer functions. And next we have to find the steady state errors for different type of inputs. So steady state error, this is the steady state error which is already defined as approaches to 0, and this is time equal to infinite. So this is the steady state error. Let's see in first example, if we have the step input. For example, in this case, if this is input is the step input, what will happen to the steady state error? R of s is equal to 1 over s. Then steady state error is simply, so if this R of s is 1 over s, then after cancel out and apply the definition of this one, and the steady state error is simply like this one. So for step input, keep in mind, it is very important, steady state error 1 over 1 plus. So this open loop transfer function at s equal to 0 is representing something else with constant value. So this is again very important, and this constant is simply, sometimes we can say this is the position constants. So for unit input, steady state error is 1 over 1 plus some constant as compared to next values. Let's observe same result in a more generic situations. For example, this is the value of the steady state error for step input. For step input, numerator value is 1 and denominator 1 plus the open loop transfer function, and even we apply this limits up to here, this gives the some constant value. So for example, if we have a open loop transfer function like this one, this is this form representing the position of poles and position of the zeros. Clearly, if we factorize the numerator and denominator terms of the closed loop open loop transfer function, and this s raised to power n representing the poles at origin, and simply we can say it is the integration part in an open loop transfer function, forward feedback. So if we take n equal to 1, then and s approaches to 0, then this value gives the some constant value. And for zero steady state error, this should be infinite. This should be infinite. Here is the just missing the value of s, and it is observed that if we take n equal to 1, then 1 over s is there, and if we put s equal to 0, then this will goes to infinite. And in this case, if we find this term is infinite, then steady state error is 0. So for this transfer function, if it is type 1 or greater than systems, then steady state error is 0 for step input. This is the final result. As in the previous example, we see if we increase the type of the systems, then steady state error, which is in last case is 1 over 2. If we take this steady state error, if we want to find the steady state error is 0, then we have to increase the forward feed loops. It means we increase the type of the systems. Similarly, this is observed in this case, that if we find the steady state error 0 for step input, if in this case, if n is greater than or equal to 1, then this term is infinite for s equal to 0. And similarly, steady state error, and for this case, steady state is 0 for n equal to or greater than 1. So this is the important result that we observed here. So summary of the step input for steady state error is simply, if the systems is type 0, then there is some constant term like this one, and if we and in this case steady state definitely equal to 1 plus constant, and it gives us some constant value. And if the type 1 systems, then this position constant is infinite and the steady state error is 0, and so on. Next, we have to find the steady state error for RAM input. For example, in our case, definition of the steady state error is S times this one, and this is the error signals, and this is the definition of steady state error. If you take this input is the RAM unit RAM, then it is equal to 1 over S square, and if we substitute 1 over S square in this relation, and we have the values of steady state error is 1, this S1 is cancelled out with this one, and we have the steady state error for RAM input is equal to this one. And if we apply the S equal to 0, then we have this type of relation. This is very important, and keep in mind it is will be used directly if we have systems, and if we want to find the steady state error for that systems for RAM input, directly we have to find the value by using this one. And this open loop transfer function is also very important. If this is the different type of this systems is changed, then the steady state error is automatically changed. So let's see again this most generic situation of the open loop transfer function. For example, in this case, this is the most factorized form of open loop transfer function, and directly we can find the position of the zeros and the poles of in a open loop transfer function. And if we have this n is equal to 0, then this is type 0 systems, and this is, if this is type 0 system, then error signals will be different, and if it is equal to 1, then error signal will be different. So if we apply this n equal to 0, then this is type 0 systems, and then if we put this open loop transfer function with type 0 here, then steady state, then g of s is 0, and error signal will be infinite. And similarly, if we take type 1 systems, if this is type 1 systems, then this s will be s raised to power 1 is s, this s is cancelled out with this s, and simply we have some constant value. We have some constant value for type 1, and again this term is infinite for equal to or greater than values of the n2. It means for type 2 and further types, this terms will be infinite, and error of steady state error will be 0. So for RAM input, steady state error will be different. If the type 0, steady state error is infinite, and similarly for type 1 there is some constant, and similarly for type 2, and this constant definitely will be infinite, and the steady state error is 0. Let's review the concept. So equal to 0 and s g of s. If this g of s is type 0, and it means if 1 over it is some constant, then if we put this s is equal to 0, then we have the 1 over 0 is equal to infinite. And similarly, if this open loop transfer function is 1 over s, type 1 system, s raised to power 1, then this s is cancelled out with this one, and there is only constant term like this time, and the steady state error is 1 over the constant. And if we increase the power of this s is, for example, s raised to power 2, then 1 is s cancelled with this one, and 1 over s representing the infinite. So this constant value is infinite, and steady state error is 0. So this is very important result which we driving, and this is if we increase the type of the systems, then steady state error for the same input will change automatically. For example, for simple RAM input, we have infinite steady state error and constant steady state error and zero steady state error. It depends on the type of the systems. So for parabolic for parabolic input, steady state error will be, for example, this is S times this one, and if this input is unit parabolic, then Laplace of 1 over s cube 2 is cancelled out with the value of the Laplace, and definitely it is equal to 1 over s cube. And if we put this as r of s input is 1 over s cube, then we have power 2. Then simply this term is definitely is 0, and this term defines the behavior of the steady state error and the type of open loop transfer function. So this is the definition, and finally we have this steady state error like this one. Let's see most generic form of the open loop transfer function. If this s raised to power is 0 here, then this term definitely is 0, and the steady state error is infinite. And similarly for s raised to power 2 or higher values of n, answer will be different. For the n raised to power 2, then this s square is cancelled out with this s square, 1 over s 1 over s square. So this 1 over s square is cancelled out with this one, and simply we have some constant value. In this case, we constant have a very different name, and if we increase the power of n, then constant value will change and the steady state error will be 0. For example, let's see in this table. For example, if the type is 0 or type 1 systems, then acceleration constant or the constant value is 0, and the steady state error is infinite. And for type 2 systems, there is a constant terms and the steady state error is also constant. For further, if we increase the type, then constant will be infinite and the steady state error will be 0. So this is the important results derived with the addition of parabolic inputs. We study that the behavior of the steady state error will be definitely changed if we increase the input of the systems. For example, if we have input is step, it is 5 times steps, height of this one is 5, then the Laplace transform is 5 over s, and the open loop transfer function is given. There is 1 0 and there are 2 poles. If we substitute in the definition of the steady state error, we have the value of the steady state error for this step is 5 times over 21. So this is the constant error. For this RAM input, if we want to find the steady state error, it is equal to infinite. And similarly for the RAM input, we have to find the value of the steady state error for parabolic input is also infinite. So these are the summary for different type of static error constants. For the if we take directly open loop transfer function and apply the limit f approaches to 0, then this constant is the position constant. And we observed in the case when there is a step input, then we have value of corresponding steady state error is 1 over 1 plus this constant. And similarly for the velocity constant, and this uh, velocity constant is defined as s times the open loop transfer function as at s is equal to 0. And this observed when we apply the RAM input, and there is the steady state error is a 1 over the constant. And similarly is the acceleration constant, and this acceleration constant is defined as s square times the open loop transfer function as at s is equal to 0. And corresponding steady state error is equal to 1 over constant when there is parabolic input. In this lecture we review some fundamental terms. If you already know the terms, then skip that portion of the lecture, and continuing with the derivation of steady state error. We start with the derivation of steady state error for unity feedback, and apply for that steady state error is observed for different type of inputs, and from there we find the some error constants, and also observed and relate the steady state error for different type of input and the error constants. So next lecture in the next lecture we will continue this type of discussion. Hopefully you will understand the lecture. If you have any queries, please forward that queries to the CR of the section or directly to me. Okay, thank you so much.